This lesson is on continuity. So we're going to determine whether or not a function is continuous at a certain point. So what do we mean by being continuous? Well, if I have a function like this and I'm interested in the point C, this function is continuous at C. There's no break at the point C. In fact, there's no break anywhere. So this is continuous everywhere on its domain. Now, we could have a situation like this where it's not continuous at the point C again. Let's put a hole in the graph. So right now, there is nothing defined for C. There is no value for f of C. I could give it a value. I could say, oh, f of C is this. So now it still satisfies the vertical line test, but this is not continuous at x equals C. So what can we say here? What's the issue? What's the difference? The value of the function here, this black dot, is not where this function is headed. Where this function seems to be headed is the limit. And the value of the limit, which should be up here, is not the same as the value of the function, which would be here. If that happens, we have a situation where the function is not continuous. Let's look at some other cases where the function is not continuous at C. So let's say that our function comes in like this, and then it jumps up here, and then it continues this way. So what we recognize here, there is a value for f of C. F of C is here, but it's heading from the left, it's heading to this point. From the right, it's heading to this point. So this is not continuous at x equals C. And that'll come down to this notion of the limit. And let's take a look at one more case. So as I approach C, from the left, it's going to infinity. From the right, it's going to infinity. This is not continuous at x equals C. So we have various types of discontinuities that we can look at. So this first one is called a removable discontinuity. And basically, what a removable discontinuity tells us is, if I could fix one point, if there'd be a way for me to fix one point, I could make it continuous, right? I could move this black dot into this spot. I could remove that hole, and all of a sudden, the graph would be connected. We'd have a continuous function at that point C. So that's called a removable discontinuity. Over here, notice we have two pieces, probably a piecewise function. This is called a jump discontinuity. So again, as I approach C from the left, it's heading to one point. As I approach C from the right, it's heading to a different point. Sometimes called an essential or a non-removable discontinuity. And this last one, it's heading to infinity or negative infinity or some version of that. In this case, both heading to positive infinity from the left and from the right. This is an infinite discontinuity. So those are different kinds of cases we can look at, different kinds of continuities. Now let's go ahead and look at a formal definition of what it means for a function to be continuous at the point x equals C. So our informal notion is that a function is continuous at C if it doesn't break there, if the graph is connected. We want to go ahead and we want to define that in terms of our concepts from calculus. So here's C, here's our function. We want it to be continuous at C. Notice there's the value f of C, if you're interested. And also notice that's the way it's headed. Well, that gives us our definition. So this function is y equals f of x. And what do we say? A function f is continuous at a point C if the following conditions hold. Number one, the limit as x approaches C of f of x has to exist. We have to have a limit, which we have. It's approaching this number. I'll call it L for now, right? As I approach from the right-hand side, the y values get closer to L. As I approach it from the left, the y values get closer and closer to L. So we do indeed have a limit. The limit is f of x, x approaches C of f of x equal L exists. So we have to have a nice limit. It can't be infinite. It has to be a real number. Number two, f of C has to exist. And three, the limit and the function have to be the same. If those three criteria are satisfied, then the function is continuous at C. So we can go ahead and look at these three conditions and relaxing them determine situations where they're not continuous. So in this case, again, this is also the point C, f of C. So the y value is f of C, but also the limit is L. As I approach from the right, the y values get closer to L. As I approach from the left, the y values get closer to L, and f of C equals L, equals that limit. That's what it means for a function to be continuous. So let's look at some cases. What if the limit doesn't exist? What kind of a situation would that be? What kind of a discontinuity would we have where the limit doesn't exist? As we approach, let's just call it 2 this time. And you can see that those numbers are not the same. So as I approach from the right, I'm hitting one number. As I approach from the left, I'm hitting another number. So the limit as x approaches 2 from the left of f of x is not the same as the limit as x approaches 2 from the right of f of x. So the limit as x approaches 2 of f of x does not exist. So what kind of a discontinuity is that? Notice this is a jump discontinuity. But the thing that failed, again, we have our three conditions to be continuous. The limit did not exist, therefore it cannot be continuous at C. Let's look at another example. Let's say I'm approaching 5 and I have a hole in the graph. There's a hole. It's broken. So what's my issue? The limit does exist. The limit is this L. As I approach from the left and the right, it's approaching the same number, but there is no value for f of 5. F of 5 does not exist. Or you could say 5 is not in the domain of the function f. If that happens, what's our conclusion? F is not continuous at 5. Continue us at x equals 5. What kind of a discontinuity is this? This is a removable discontinuity because, again, with 1, I could fill in one single point. and that would make the limit exist. So we say this is a removable discontinuity. Discontinuity, T-I-N-U-I-T-Y. Okay, now what about if the fact that the limit and the value of the function are different? Actually, I need to do one more where the limit doesn't exist, of course. Let's take a look at this case. We're approaching 4 and it's an asymptote. So let's have the function heading this way here. And maybe heading this way here. So what's going on here? We don't have a limit at 4. Again, it's broken, it's in 2 pieces. The limit as x approaches 4 of f of x does not exist. But in this case, well, the fact that it's positive infinity from one side and negative infinity from the other doesn't really make a difference. If the limit is infinity, it still does not exist. The limit as x approaches 4 of f of x does not exist, so f is not continuous. Continuous at x equals 4. What kind of a discontinuity is this? This, of course, is an infinite discontinuity. We'll abbreviate. And I want to look at one other case. We're approaching 3. So there's the limit that it's approaching, but the value of the function is here. Okay. So again, what we can say here is the limit as x approaches 3 of f of x is L, but f of 3 is down here is not L, is not the same as f of 3, right? So this is not continuous at 3. And this is another example of a removable discontinuity. Okay, so our basic idea, let's keep in mind our rule that we're working with here. A function is continuous at a point C if the limit as x approaches C of f of x equals L. That limit exists, if f of C exists, and if that limit is the same as the value of the function. That's what we want to have. Well, I want to talk a little bit about left and right continuous. We can have a situation where something is not continuous, but it is left or right continuous. So what does it mean for a function to be continuous from the right? Well, we'll say here a function is continuous from the right at C if the limit as x approaches C from the right of f of x equals f of C. So as I approach x from the right, we're heading towards this value L. As I approach it from the right, it lands on the dot, which is the same as f of C. So notice in this case, the limit as x approaches C from the right of f of x equals L. Also notice f of C equals L. So what are we going to say? So this function is continuous from the right at C. But what would it mean to be continuous from the left? So how would we define that? Well, we just switched that one little bit from approaching C from the right to approaching C from the left. A function is continuous from the left at C if the limit as x approaches C from the left, limit as x approaches C from the left of f of x equals f of C. And you'll notice this example I have here is not continuous from the left, because as I approach from the left, I hit this other point, right? I will call this little l. So on this one, the limit as I approach C from the left, the limit as x approaches C from the left of f of x equals little l, which is not the same as f of c. So that is not going to be continuous from the left. If I want to make one that is continuous from the left, what would my graph look like? Continuous from the left. So as I approach from the left, it's got to land at the limit. Here's a point C. As I approach from the left, it's got to land at the limit. So notice that this situation, if I call this little l again, is to be consistent with my previous diagram. The limit as I approach c from the left is the same as f of c. So this is continuous from the left at c.